Last class we were discussing about the Roth stability criterion. So here we already seen that what is bounded input, bounded output stability, and what is meant by asymptotic stability. Then we saw the response contributed by various types of roots. So if the transfer function is given, you need to find the denominator and you have to equate to 0. Then you will get the location of the poles. For example, here, as you can see here, m of s is equal to a by s plus a. When you are equating the denominator to 0, s is equal to minus a. It is in the left half plane. Normally, if the poles are on left half plane, you know that it will be it is a stable system. If it comes on the right hand side, see the exponentially increase, that means it won't converge. That is why it is not a stable system. So normally the characteristic equations, the last class, because of the speed, the characteristics pronunciations you may feel little odd. Let it be okay. Again, in this case, when you are equating the denominator to 0, you will get pole at minus a plus jb and minus a minus jb. So in this case also, it is a damping. So finally, it will reach as a 0. So it is a stable system. And in this case, the poles are coming on the right hand side. When you are equating the denominator to 0, here is s is equal to plus a minus jb, here s is equal to plus a plus jb. So this and this poles, this will be on the right hand side. So you know that the response is increasing, and response equation also you can see. And when you are coming in this case, that means if the poles on conjugate poles on y-axis, that is s is equal to minus jb and s is equal to plus jb. When you're equating this to 0, this is 0, you are getting m of t is equal to 2a cos bt. So it is a sinusoidal signal with a constant amplitude. If in this case a divided by s plus jb all square plus a divided by s minus jb all square, in this case you can see that multiple conjugate poles on j omega axis. In that case, you can see that the oscillatory the response is in time domain. It is oscillatory and the amplitude is constantly increasing. M of t is equal to 2at cos bt. Now, when you are coming to expression like this, when you are equating the denominator to 0, s is equal to 0. So it is coming at the origin of the S plane. S plane consists of sigma plus j omega. Now in this case, you will get your response will be a constant, okay, with respect to time with the amplitude a. Now when you are dealing with m of s is equal to a s square, you can see that multiple poles at the origin. In this case, you can see that it is linearly increasing. So we already come across that this case, that means m of s a by s, it is an integrator circuit. When you are integrating, you are getting it is equal to a. So this is an integrator circuit. Okay. Yeah. When you are integrating, yes. So when you are this is an integrator, it is not stable, or you can say that it is marginally stable. And when you are coming the case this also, that is a conjugate poles on the imaginary axis, then you can see that response is oscillatory and this also marginally stable. So from this we can say that if all the roots of the character equation have a negative real parts, then input response is bounded and eventually decreases to 0. So system is bounded input and bounded output stable. If the roots of the characteristic equation has a positive real part, then g of t is unbounded and the system is unstable. That means if it is on the right hand side. If the characteristic equation has a repeated roots on the JM axis, the system is again unstable. One or more non-repeated roots of the characteristic equation are on the JM axis, then also the system is unstable. The conclusion of Now necessary conditions for stability that we discussed. In this case, we studied that all the coefficient of its characteristic equation be real and have the same sign. All the coefficient of the characteristic equation be real and have the same sign. None of the coefficients should be 0. That is the condition, necessary condition for the stability. Then after that, we analyzed many examples like this. As you can see that we analyzed many examples like this. When you are observing this, here it is s raised to 3 terms is missing, so it is unstable. In this case, there is sign change, so it is unstable. Here also sign change as well as some of the terms are missing, so it is also unstable. And here also you can see that some of the terms, the constant is missing, so this is unstable. And here in this example we analyzed the transfer function is given. We have to see the characteristic equation, and you can see that if the roots are coming on the right half of S plane, roots of the characteristic equations, that means the denominator is coming on the right half of S plane, then it is unstable. If roots are on the left half of S plane, then left half of S plane, then it is stable. And we analyzed these examples. Then we came to root stability criteria. So here, as you can see that this is a characteristic equation with that is equated to 0. Now, which one is the highest power? So here S8 is the highest power. So you have to write here S8, then S7. Okay, so here alternate coefficient you have to write A0, then A2, then A4 from here. First one, then not next, next to next, then again next to next, like that. You have to first make a first row. Second row is the second coefficient, and next to next, that is A3. Then you can see A5, like that. You need to form the coefficients. As you can see that once you form the coefficients, once you arrange the first two rows, the next element in next row or elements in next row can be found by considering the coefficient in the above two rows in the first column, considering the elements of the first column of above two rows, that you have to give the high importance, and from this, for example, a1 into a2 minus a0 by a3 divided by a1. That is the first element in the third row. Then you have to compare this with the next to next. That means a1 into a2 minus a0, a0 into a5 divided by a1. Then next element is calculated this with this. That means down a1 into a6 minus a0 into a7, like that. You have to form as we go through this table. So go through the table, you can see how the root table or root array is formed. You can see that how the root table and root array is formed, and many last terms almost everywhere it is you can see the structure how it is happened. And here there are two necessary conditions the system to be stable. Each items of the first column of the root array of its characteristic equation be positive. That means all the elements in this column should be positive. That is the first conditions. If this condition is not met, and the system is unstable. Now, if this condition is not met, that means all the elements in the first column is 0. That condition, if it is not met, then the system is unstable. Then you can find the number of roots of the characteristic equations in the right half of plane. You can find it. How you can find it? You have to see that how many sign changes. Suppose if this is plus, this is with them. This is having a sign of plus. This is having minus. This is having plus. This is having minus. Remaining all plus. Then you can see from here to here one sign change. From here to here another sign change. From here to here another sign change. From here to here minus sign change. That much roots are on the right half of S plane. Now the first difficulty we discussed. What is the first difficulty? The first element in any of the row of the root array is 0, while the rest of the row has at least one non-zero element. Okay, in that case, what you need to do this, you have to replace the first element in the root table, which is 0, by epsilon, parameter epsilon. Then you have to, using epsilon, you need to develop the array, and after developed, you have to so once it becomes 0, there itself you can understand that system is unstable. But we are doing further analysis to see that how many roots are, or how many poles are on the right half of S plane. For that, what we need to do is we need to make eta tending to 0 the number of sign changes in the element of the first column of root array indicates the number of roots of its characteristic equation in the right half of S plane. Even if there is no sign changes, the system is unstable and there are roots in the imaginary axis. So that is the important thing. You can open this book. When I am explaining it, you can go through the your text also. And this is one way. Another way what we can do is, once the first element in the column of any row becomes 0 and remaining elements in that row is non-zero, in that case it is there itself, it is unstable. But we need to find the how many poles are on the right half of S plane. For that, what you need to do is we have to modify, we need to modify modified characterization in Z by replacing S by 1 by Z, from the root array Z. Now number of Z roots with the positive real parts, that is in the right half of Z plane, are same as number of S roots with the positive real parts. So when you are having any root with the positive real part, you can understand that that is on the right half of S plane.